So in this case, it's just a rule. There is a function whose derivative is 1 over x squared plus 1. You might know it as 1 over 1 plus x squared. Does anybody remember? Inverse tangent. So you're right, it had trig in it. So I'll write arctan. All right.
Now that I think about it, cosine was a really bad guess.
Yes, yeah. Yeah, anything with an arc would have been fine, but yeah, cosine was not the best word. So sometimes it's just a rule, right? Sometimes it's a process. So in the case of the second one, you can see how we've increased the order of the numerator, but the denominator has remained the same. So it still has a similar look, but it's going to be a completely different approach. It's not going to be an arctangent. Right? So let's take a quick look at that one. Because why not? So when you're dealing with a fraction, one strategy might be to take a look at the denominator and see if its derivative is equal to the numerator. Is that the case here?
No.
Yeah, if that's the case, then we're looking at something that's in the form of u prime over u. What function has a derivative that's u prime over u? I believe I wrote it here yesterday.
Guess.
It's not inverse trig. Natural log. Okay, so natural log of x squared plus 1. Now I put the absolutes there, even though in this case I wouldn't need them. How do we know I wouldn't need them in this case?
Positive.
It's going to be positive no matter what. It's a sum of squares. Right? If you're adding two positive numbers, it's going to be positive no matter how you slice it. Right? So the derivative of the natural log of x squared plus 1 would be 1 over x squared plus 1 times 2x. So that's a perfect fit. Now if the numerator were some other constant multiple of x, then you may want to use u substitution. But even so, you might not necessarily want to do that. All right, the last one though, all bets are off. Because that doesn't fit a rule. It's not a natural log. Again, you're only thinking natural log when the numerator is in some fashion a derivative of the denominator. Right? So it's only off by a scalar multiple or a constant multiple. So not the case here, because it would have to be some multiplier of x, not x squared on the top. All right, so that's not going to work. Two possibilities. One would be actually to use long division. I don't know if you remember that from pre-calc. Maybe the only thing you remember about it is that you didn't really like it. That's a possibility. I'm going to show you a clever little strategy here that that may do what you want it to do. All right, so I'm going to rewrite. Right. I'll put the dx in a minute. But what I want to do is somehow manipulate this fraction. Right? You can think in terms of conjugates and stuff like that, but it doesn't really get you anywhere. If I add a 1 to the numerator, I would be making the numerator and the denominator exactly the same, right? That would be great if that were the case, if I were allowed to do that. I'm not allowed to just add a 1 to part of a fraction, or even both parts of a fraction. It would completely change the value. If I had like 2/3 and added 1 to the top and the bottom, it would become 3/4. That's 2/3 and 3/4 are not the same, so that wouldn't work. So this is a completely illegal move, unless I do that. And that's why I wrote it on the board. Yeah. So, okay, cool. Wonderful information. Now what? circle this because I can split my fraction up by that subtraction sign. And what that's going to do is create an equivalent relation, or expression really. 1 minus 1 over x squared plus 1 dx. Now I can integrate each part individually. So the antiderivative of 1 is just an x, and the antiderivative of 1 over x squared plus 1? Arc tan x, with the negative sign in front of it, plus c. All right. Now, if you rewrote it so that the negative was in the numerator, so 1 plus negative 1 over x squared plus 1, what would the antiderivative be? Arc cotangent. Right? So you can get a couple of different answers out of this. You might say x plus arc cotangent of x plus c. All right, equivalent answer. Right? But you know, it's a different strategy. Now, it falls under the category, I think, of I don't know that I ever would have thought to do that. And my answer to that would be, well, you didn't think to use the law of cosines, for example, until you were shown that either. So, you know, sometimes you need to be shown something first before you realize it's a strategy that you can use. Right? This is a situation that applies specifically when you have the exact same term in the numerator and the denominator. All right, that's your indicator that this might be the course of action to take. There's actually another way that you can go about doing this exact same problem. Just a lot more complicated. A lot more complicated, like a page of work. It's fun, and I'll actually revisit this problem when we're dealing with that particular topic, just to show you, because it's kind of fun. But obviously, you know, the shortest distance between 2 points is a straight line. You want to go with the simpler approach. All right. So 3 very similar integrals, but 3 wildly different results. All right. Yeah, so anyway, in case you forgot your inverse trig rules, they're right there, and they are very useful. So if you had them memorized at one point and you kind of lost it, this is an opportunity to bring them back. All right, so definitely take some time and study them. Flashcards are definitely a good resource when it comes to that. So strategy. So we'll kind of break it down a little bit more. One strategy is that you can separate the numerator. All right, that only happens if you have a sum or difference within the numerator. Right? So in the last example, we created the sum and the difference. Right? Sometimes it's just flat out given to you. If that's the case, you could just kind of jump right to it. So in this case, we're looking at x over the square root of 1 minus x squared dx plus 1 over the square root of 1 minus x squared dx. You can contain it all in one integral if you want. I just separated it here to really accentuate the differences because I wanted it to become painfully obvious that the second integral matches up perfectly with one of the rules. All right? So we already know that part. Right? I found historically that people tend to struggle not with this part because that's procedural. You struggle with this part because that requires you to know something, right? A fact. Right, memorization. So that's where people tend to fall short when it comes to stuff like this. All right, so we already know that we have the second part of this integral taken care of. So the first part, it definitely doesn't look like a log, right? Or at least not in its current form. if I were to take the derivative of the bottom of the fraction, that would involve chain rule. There's no way you're getting an x out of that. Right? You're going to get something with a radical in it. So our only choices are u substitution or integration by parts, so let's try the u sub. U would be equal to what? 1 minus x squared, making du equal to negative 2x dx. I don't need the negative 2, so let's make it negative 1/2 du equals x dx. That could be a mental step if you want. You can go right from the du equals negative 2x dx to your substitution. I just find that it can be a little trickier to see it unless you actually do the work. In a lot of cases, not in all cases. So negative 1/2 du over the root of u, but you want to clean that up because that's not a convenient form. Negative 1/2 u to the negative 1/2 du, which integrates to what? Negative u to the 1/2. And we'll do the whole plus c business in a couple of minutes. All right. So we'll pop back our u, which was 1 minus x squared. So we're looking at negative 1 minus x squared to the 1/2. The other part was the inverse sine, right? So arc sine plus c. All right, so again, a lot of moving parts, but nothing too crazy once you get that first step out of the way. All right, that's really the key ingredient, and you're going to find that that's a recurring theme throughout the entire unit, or at least from here on out. That once you get your first step out of the way, you have a plan of attack, and then after that, everything's fine. Oh, I left the water in the car overnight. It's crunchy. Ah.